What was that curve?
Yes.
Did you get a chance? Okay.
Ridiculous.
So I did a little bit, not a little bit actually. That was like a crane. Like this. Okay, so all the questions goes from the notes. Like I can get question by question from the notes. If you study the notes, you'll find the first question, second question, all of them. So you have to revise your notes carefully for the exam. Because this is the first thing that I look at. You know, I opened the textbook, I found, this question is very difficult. You will not be able to, okay, let's go back to the notes. I go back to the notes, I found the question. Maybe I make it more easier so that you don't solve more steps. And I just cut some parts and then give you the question. So if you study the notes, you should be able to solve the problem. Alright, so I'm not sure if you guys saw my announcement from yesterday. The exam is going to be at the same time that we agreed on next week on Thursday, but it's going to be from 9:30 to 11:30 because there's another exam at 12. So it's already set up by the university. Okay? So it's 2 hours exam. I believe we're going to have like 5 full questions, maybe 5 or more. So prepare yourself. It's going to cover the entire class, fluid mechanics, dynamics. So you study very hard. If I'm going to study for this class and about to take an exam for dynamics, what I do is, how many chapters did we cover? We covered 4 chapters for particle dynamics and 2 chapters for rigid body dynamics and 1 chapter for fluid dynamics. So we have a total of 7 chapters. So what I do, you have 10 days. Every day you revise a chapter, and every chapter you solve maybe at least 2 problems that test you how are you in this chapter, how did you comprehend this chapter. So 7 days you will be finishing the 7 chapters, okay? Like by the end of this week we will end at chapter number 7. So when you finish to the last one, so you revise 7 chapters. And then the reminder, the 2 days before the exam, like from Tuesday to Thursday you have 2 days. You need to solve comprehensive problems. You pick any problems in any chapter, randomly. Because this is what the exam is gonna give you, like it's gonna be a random questions. You're not, because I believe, was what I'm seeing right now, when you have a question, is that a particle dynamics or is it a rigid body dynamics? Is that, should I solve it with work or should I solve it with energy? I'm not gonna tell you what a chapter it is, but you need to figure it out, how you can solve it. And actually some problems, it can be solved by work and energy, some problems can be solved, most of them are valid solutions, okay? So you need to pick a random question from the textbook and try to solve them in the last 2 days. So my advice is to start your revision right now. Dynamics is a very, we didn't take 2 chapters in rigid body dynamics because we covered other stuff. But my advice is to start revise right now, every day, like starting tomorrow. Okay, I'm gonna revise chapter number 12, the day after chapter number 13, and do them chapter by chapter so that you can revise the 7 topics or the 7 chapters that we have before, 2 days before the exam. And in the 2 days before the exam, can be the general revision, okay? So, and the way that I'm gonna start for this, I cannot like write everything, like you cannot write everything. You need to read because there's no time, okay? Because one time I tried to do this with fluid dynamics back in the days and I didn't finish. And there's a lot of topic that I didn't cover. So you need to learn how to study for final exams. It's completely, it doesn't matter how smart you are, whatever study mechanism, there's a way to study for final exams so that you get the best grades, okay? So there's difference between being a smart and being able to get points and get grades. That's completely different. So you need to have a strategy, especially for subjects like dynamics, because it's a very big subject. So you need to read through, understand the concept, and understand the equation sheet that you have. Know what is each equation do. You need to understand that you have an equation sheet. Actually, if you know what every equation what can do for you, you will solve the exam because it has everything for you. Okay, so you need to understand while you are studying for each chapter, have the equation sheet in front of you. These equations are for this. Maybe you write some notes. Okay, to solve this, to solve this, to solve that, you write on the equation sheet because it's gonna be like a maze. The equation sheet, you don't know what can do for you. But if you know every equation what can do for you, you will be able to solve the exam. All what you have to do is to understand the problem and know what chapter that this problem belongs for. And number 3 is to know what equations that you should use, because all the equations that you need to use to solve the problem are in the equation sheet. That's all what you want to do. Okay? Back in the days, I didn't have any equation sheets. You need to remind, you have an equation sheet right now, and you can use it. Use all the equations that you have here. So please have this in mind. So the exam is like 10 days from now. I wish that you all will do great in the exam. I did my best. I'm trying to do my best. You don't know how hard I was like the day before I come to the class preparing the notes and trying, like when I prepare this class, I was trying to find the best way to put the things on the board so that you can understand it in the best and the simple way. Like I tried, okay, how can I do this? How can I do this? Should I use something? Should I buy something so that I can demonstrate for you? So that's the thought. So I'm doing my best, so you have to do your part. You have to do your best as well. Okay, so this is for that. The criteria for the grading is 95% is for A, right? That's what we have right now. And based on this and based on the grades that we have, even with curving, I found like it's gonna be 3 or 2 is gonna get A, given that you got A in the final exam. Maybe I'm gonna change that, depends on what you are gonna do. But what the criteria that we have right now, A is 95%, A minus is from 90 to 95, but this might get a change. At least I need 10% or 15% of the class can get A. So this might change. Don't think about it. I will get you as much as you deserve, but you need to help yourself first before I help you, okay? All right, so let's continue chapter 17. I uploaded the model answer for the exam. So you guys, I'm gonna give you the exam sheet after. If you have any questions, by the way, the curving might change. How? Because some of you are gonna come back to my office and say, okay, I have some points and claim some points. Maybe he will have 10 more, maybe he will have 5 more. So based on this, the whole curving is gonna change. Maybe a little bit, maybe 1 more point, 2 more point, 3 point less, so it depends, okay? Yeah, because some of you are gonna get more points, so they are increase the curve. So we need to lower. So if you feel that you deserve more points than what you have, and actually in the model answer I put like like if we have like this question 25 points, I said this is 5, this is 10, this is 5, this is 5. So if you feel that you put some pieces that you didn't grade for, just come back to my office and you can get your points back, okay? Right.
Okay, I was wondering, so should we review like the exams more than the quizzes, or should we review them less? Like where does the exams rank?
Oh, you mean like the midterm exams that we got?
Yeah, so it goes like notes, and then would midterm exams be like second? Or?
Well, definitely you will get questions different from the midterm exams, but midterm exams is gonna help you to learn from your mistakes. Okay, what did I do here that I shouldn't do in the final exam? And also quizzes. So you need to look at these, but first you need to understand the lecture notes and the examples in the lecture notes. That's number 1. You finish them, go to the next level. Check the exams, check the quizzes, and then check the homeworks. Because when I'm putting the exam, this questions you already got it in the midterm. So let's look at the homeworks. Because I know most of you, a big percentage of you, I'm not sure how they solve the homework. So this is how it's gonna show that you solve the homework or not, okay? So homeworks is also one of the most important things that you need to revise. You need to understand every question that you solve in your homework. And that's a lot of things, right? The notes, you guys have lots of exams still now. You know how to study for the exam, but mechanics, I'm sure it's big. It's as bigger than any other class that you have taken before. So you need to have different strategy. So the different strategy is to allocate time that you can read the notes, understand what is in the note, and then read the questions. All what you have to do is just look at the homeworks and know the idea of the problem. Because every problem has an idea. You don't have to solve it by your hand. Maybe you pick one problem in the homework that you feel that you are not 100% about it, so you start to solve it, okay? And once you start to solve it, you will know what you are lacking. So there you go, revise and understand. If you have any problem solving the problem, email me and we can meet, we can have a Zoom meeting and we can think about it together. Does anyone have any other questions? All right, so last time I spent the whole lecture talking about the, what did we talk about? Do you guys remember? Mass moment of inertia. We distinguish between mass moment of inertia and area moment of inertia. Do you guys remember the difference? The mass moment of inertia is the resistance of the body to rotation. Like if this mass, like if I have any body like this, so what is the resistance of this body to rotate, okay? But if we are talking about area moment of inertia, and that's what we do in structure analysis or in design, it is the resistance of body to bending moment. Like how this area is resisting the bending moment that happens on this cross section. Okay, for the mass moment of inertia, I showed to you how to calculate the mass moment of inertia from Durston principle, and you should understand this. You should understand it 100%. But all what I wanted you to know, what axis that we are looking at. Like if we are looking at the resistance of this mass to rotate about the z-axis, so there's something like this mass is bent here and can rotate here. So that's why we need to look at Iz of the body. But if we are looking at the mass to rotate about another axis, so this is x-axis, so this is the axis of rotation, like this mass is here. Like let's look at this door. This door, if we are talking about the mass moment of inertia, if we are saying this is x, this is xy, and this is x is coming out of this door. Okay, here we go. Yeah, so this door, what is the mass moment of inertia that we are looking at? If I'm saying this is x and this is y. Z, that means that this door is rotating this way. When we open this door, do we rotate this door this way? It doesn't rotate about Z. I'm saying this is x and this is y. What is rotating about? Y. It's rotating about y, but y is here. It's rotating about the axis parallel to y. This axis, right? But if this door is bent here and bent down there, so it's rotating about y, the CG. So if you want to find the mass moment of inertia about this door, about this axis, so you need to get the mass moment of inertia about the xy, which is, you can find it in the table, and then transfer it from here to here. How we can transfer it is the mass multiplied by the distance squared. Okay, this is the same thing that we do here. So this is, if this door, like this is the door, and it's rotating about this point, so it's about y, right? But if it's rotating about this point, it's about y, but it's a parallel axis, so we need to apply the parallel axis theorem, right? But if this door is rotating about this, so it's about x, right? But if I'm rotating about this, so it's about a parallel axis to x, right? If I'm bend this door here, so it's rotating about z. That's what you need to understand. Look at your problem, understand how the mass is rotating. Like last time, I had a bar like this, and this bar is bent here, and I'm telling you that this is, for example, xx, and this is xy, and this is xz. If I want to solve this problem, and I have I in the problem, I should be I what? This is a bar, and this bar is going to rotate about what axis? About xx, y, or z? It's going to rotate about z, right? So this is z, and this is rotating about the x outside the plane, but it's a little bit shifted here. Okay, so that's
when you apply the distance.
yeah, the distance, the mass multiplied by the distance squared. And actually, in the equation sheet, let me look if I have it here. Does any of you have the equation sheet? All right, thank you. So in the equation sheet, I believe in the bar, it gives you ix, iy about two axes. One of them is the CG, and one of them is the n. Because most of the problems that is given in that we are going to solve, the bar is fixed, is pinned at the end. So that's why you are given izz, just izz, and actually ixx and iyy about this. But make sure that you look at the axes, what the axes that you have here. So you need to make sure what axis that I'm looking at. Maybe it's different axis, but you understand the concept, okay? All right, so that's what I was trying to do last time, is to understand what moment of inertia that we are looking at. Same thing when you deal with the structure analysis, next semester or whatever semester you're gonna take structure analysis, if my cross section is bending this way, so we are talking about IX, okay? But if my cross section is bending this way, so we are talking about IY because it's bending about Y axis. But if my cross section has a torsion like this, like my cross section is doing something like this, so it's about Z. That's why every time that we deal with beams or slabs that has torsion, we always look at the IZ of the cross section. That's what resists the torsion on the structural elements. All right, so that's what we did last time. And another concept that I want to make sure about. One thing that I need to make sure, do you guys know Newton's second law? What is this law? The sum of the forces equal to m multiplied by a. That's a really, really important law that we use in structural analysis, we use in dynamics, we use in everything. And if we have x-axis, so it's going to be sum fx equal max, sum fy equal may. And this concept, we use it in a structure analysis all the time. Like if we have any structure, if we have a bridge like this, and this bridge is supported, for example, on beams, and you have a roller here. When we solve this structure, and this structure has a system of loads, any system of loads, like concentrated loads, distributed loads, whatever loads that we are going to have, what we do is, we say that this structure has some fx is also max. But when we solve the structure analysis, there is no acceleration. Our structure doesn't move. So that's why this part is always 0, max. And same way, sum fy is equal 0. Because if a structure has an acceleration, that's not structure anymore. That's a mechanism that is moved. So that's why when you take structure analysis and solve something like this, you have the loads, you get the reactions here, and there's an x reaction, and you say sum of x equal to 0, sum fy equal to 0, you solve your structure. There is no acceleration here, that's why we put zeros.
I was going to ask per moment, why, I know we've always used it like the sum of moments are equal to 0, but why in this case? Like what's the equation for it?
Sum of the moments equal to 0. Sum of the moment is always equal to I bar multiplied by alpha. But this structure cannot rotate, it doesn't have any alpha. So the alpha is already 0. So that's what our structure is. So our problems, it looks simple. It's more simpler than dynamics from my perspective. However, they have some complications when we calculate bending moment and shear force diagram and lots of other stuff that we do. But here with dynamics, because it's dynamics, not structures. So something that is moving, so that's why we always keep AX and AY. One other thing, maybe we talk about it when we move forward. So let me write this rules. When we talk about rigid body, not structure, rigid body dynamics. So you have to do the same thing that you did with the particles. You need to draw a free body diagram and draw the kinetic diagram. So the free body diagram, let's say that I have a rigid body like this, and maybe we can make it general. Like something any shape, and here's something any shape. And I'm gonna do a free body diagram here, and I'm gonna do kinetic diagram here. Right? So the free body diagram, what we do in a free body diagram, we put all the forces on the object, if you guys remember. All the forces in rigid bodies, it might have a force like this, like let's say F1, a force like that, F2, a force like that, F3, but also can have moments. I can have concentrated moments at any point. And the most important thing about the rigid body is the center of mass. I need to know where is the location of the center of mass. So I'm gonna go to center of mass something like this, and I'm gonna call it G. So that's what we do in a free body diagram. We put all the forces on the structure. However, in some problems, you might be given that this body is pinned here, for example. like there is a support that support their structure here. So you need to put reaction on the support. Like I say, for example, this is my body, and I bend this body here. So this body is restrained from moving in x-axis or moving in y-axis, but it can rotate. Okay. So what is the reaction, the possible reaction at this support? Let's say that this support is A. Okay, so the reaction, for example, Ry at A and maybe Rx at A. So you need to put the reaction at this support. So you put all the forces and also the weight of the body. If you have W, you put W as well. All the forces. If you guys remember, we have, from last time, you have a body like this, is moving, so we put W with reaction. If it's moving this way, so I put FF, right? And I put the normal force. We put all the normal forces in the free body diagram. That's also what we do with rigid body. We put all the forces, okay? So what we do on kinetic diagrams, do you guys remember? We also have the CG, we put the movement. This body, I'm gonna assume, I don't know where this body is gonna move. I'm gonna assume, for example, this body is gonna move MAX, MAY, and I'm gonna put bar because I'm looking at the CG movement, okay? And I'm gonna assume this body is gonna rotate this way. And when we put the rotation, we replace the mass with the I bar and multiply it by alpha, okay? So that's the three movement that I'm looking for. If you put all these system of forces, all external forces along with the weight and the reaction is gonna result in this movement. And then using these two diagrams, you can apply Newton's second law, and it's gonna be the sum of Fx is equal to M Ax at the CG, the sum of Fy is equal to M Ay at the CG. So I put it bar, you can put it G, and we can actually make it as vectors. And the sum of the moment mg is equal to I bar multiplied by alpha. Okay? Alright. But what if I want to get not the moment at G? What if, for example, because if I get the moment at G, sometimes we pick the point that we take the moment that give me an easier way to get the moment. Sometimes the center of mass of the body is not the easiest location to get the moment. For example, solving a structure, and I want to get the moment, actually the moment at any point here is equal to 0. Okay, so you can say, okay, I'm going to take the moment here. But when you take the moment here, you will end up having an unknown R1 and an unknown R2. But if I take the moment here, I'm canceling R1 because R1 passed with the point that I'm taking the moment at. So I only end up with one unknown. Solving one equation, one unknown is much simpler. Same way here. Sometimes taking the moment at the CG is not gonna solve my problem. It's gonna make it more complicated because I will end up with more unknowns. But if I take the moment at this point, a general point, I'm gonna cancel Rx and Ry from my equation, which they usually are unknown, and I make my problem simpler. But how can I take the moment about a general point, not the center of mass, not G, like let's say point? It's always equal to I bar multiplied by alpha plus Rg with respect to any point, and this is a vector cross product, the mass multiplied by the acceleration. How? Okay, so what we did here, we said that the sum of Fx and also the sum at the moment at G, here, when I take the moment at G, I'm canceling Ax. That's what we did. Like, when I take the moment here, Max is passing to this point and May is passing to this point. I'm only ending up with this moment. But let's say, for example, this body is moving this way, and I want to take the moment about any general point here. Let's say at this point, B. If you want to take the moment about B and looking at all these movements, so all what you're getting right now, the moment of Ax and the moment of Ay is not 0. Let's say that we have a magnitude or a resultant that it goes this way. Let's say this is Ma bar. When you get Max, Ma bar is the magnitude. You guys, the magnitude A bar is the root of ax squared plus ay squared, and the direction is the sine theta. So we can get the magnitude of these two. So if you want to get the moment about this point, you need to get this moment, I bar alpha, plus max multiplied by the distance from here, and may multiplied by the distance from here. Or you multiply the resultant by this distance. Okay? So you get the moment of ma bar about this point. That's what we did here. RG, like RGD can be any, like can be like something, for example, let me put it here. If you have a point here, and if you have a force applying on a point like this, F, okay? F can be is equal to ma, but let's not focus on this. Okay? It's F. And I want to get the moment of F about this point, and this is the point of application G. So what we do, usually what you get a perpendicular, right? And let's say it's D, and the moment about point O is equal to F multiplied by D, right? That's what we do. But the general rule for this is, if you want to get the moment M at O, you get the vector RG with respect to O, and you have the force vector, and you multiply RG with respect to O, cross product F, and it's the same thing. Let's see what is the definition of the cross product. If we want to get the magnitude is going to be the magnitude of RG with respect to O, multiplied by the magnitude of the force, multiplied by sine theta. Let's find what is RG multiplied by sine theta. This is RG, and the theta is the angle between the two forces, this angle, theta. Sine theta, if you find D is equal to RG with respect to O, sine theta, because this is the diagonal, and this is the angle theta. So we can replace these two with D. So you have F multiplied by D. So it's the same thing. That's what we did here. So this is the general rule, is the moment that I already have, plus the moment that comes from these two. Okay? The more that I get closer to G, the more that the moment comes from the acceleration is less until I get to this point. So the moment from these two is going to be 0, and I only left out with I bar alpha. Okay? All right, so I have these general rules, but we have some special cases. So this is the special rule for any body under a general motion, like rotation, translation at the same time. So let's see the special cases that we have. Like if you have a translation motion, in translation motion, so your body is something like this, and is translating, for example, on this line. The CG moved it from here and came here. So there's only translation. It doesn't rotate. This is my body. Let's move it this way. So I have max, may, but the moment mg, I bar alpha is equal to 0. So this part is not there, because alpha is 0, so everything is going to be 0. So I have sum of fx is going to be equal to m ax bar. The sum of fy is equal to m multiplied by ay bar. But the moment about g here, this g, because this body doesn't translate, so mg is equal to 0. However, if you want to get the moment about any point, like point here or point there, so the sum of the moment about any point P is I'm gonna be left with this part. I alpha is equal to 0, however, this doesn't equal to 0. Why? Because I have this body's moving with a mass multiplied by acceleration, which is the force. This way, the moment about this point is not 0 because I have this distance. But the moment about G is 0 because the mass multiplied by the acceleration is passing by this point. The arm of the force is equal to 0 at G. So here, I'm gonna have 0, which, let's actually write the whole equation, I bar multiplied by alpha plus R vector crossed by MA vector. This part is 0, so I will be left by R vector with RG with respect to D, cross product by M A vector. an A vector that has AX and AY. Right, so this, if I have a translation motion, and we call it sometimes linear motion. Number two, if I have curvilinear translation. Curvilinear translation, so my body something like this, and rather than moving on a straight line, it's moving on a curved line. But let me ask you, is this body rotating about itself? It doesn't rotate about itself. It doesn't rotate this way. It just moves on a track, like a particle is moving on a track. So as a body itself doesn't have alpha, but it's moving around something. Okay? So it translate. We call it curvilinear translation. So it's still translation, not rotation. There's difference between translation and rotation. So it's still curvilinear translation. So I'm gonna have here some fx is equal to, rather than saying max, here we use doesn't say x, we say normal, and here's a normal, cg, some f tangent, equal ma tangent, and the moment about g is 0. Why? Because this body doesn't rotate about g, so the moment about g is equal to 0. So it's still the same like this, but rather than having xy, because it was translation, right now I have curvilinear translation, so I have tangent normal. Yes.
I have a question. Besides, I don't think it's related to this, but with the moon, it kind of rotates around the Earth, but it's rotating to
around
itself.
itself.
Right?
So it has a general motion.
Yeah.
So that's also we can talk about. Actually, I believe there's an application in the textbook. If you look at Hitler's book, there's a chapter that shows the application of what we learned on the moon and the Earth and how the movement look like. Maybe you look at this chapter. Okay, so getting back here, so I have mg is equal to 0 because this body is not rotating about itself and just making translation. But if I get a moment about any point, some mb. Let's say that this point, for example, here, you will do the same thing. You will get the summation of rg with respect to b cross product by ma. So you need to find a, like for example, if this body is rotating, so I have, this is man, and it's going this way, so this is ma tangent. You need to get the moment of these two about these points, or you get the resultant, for example here, ma, and multiply the resultant by the vertical distance. Okay, so that's the rules that we have for the curvilinear translation. The number 3 is the fixed axis rotation. Fixed axis rotation. For the fixed axis rotation, let's say my body's like this, and my body's fixed at the CG here, and can rotate about the CG. So the sum of fx is equal to the sum of fy is equal to, and I want to get also the sum of the moment about you guys tell me if this body CG, this is my body, and this is the CG, and I put my finger like this, and I make it all. What is the sum of fx and what is the sum of fy? 0, right? Because it's not gonna move, right? It doesn't have any acceleration. Like the CG doesn't have an acceleration, so the body's not gonna move. So this is 0 and 0. However, it can rotate because this is bin, okay, not fixed. So it can rotate, so I can still have I bar multiplied by alpha. These two. Alright, so but here, this is, we can call it number 4. General plane motion. General plane motion that has fx, have fy, have mg, have also the moment about any point. So the body can move and also can rotate. Okay, so this is the an application to this. If you have, for example, like, let me put it here, a pulley, something like this, and it's attached to a cord, and you somehow you pull this way, so this is rotating and also translating. So this pulley is rotating this way and also going up, so it makes rotation and translation. So it has AX, maybe, it doesn't have AX, it moves AY, so I can't put AX as 0, it has AY, has alpha because it's rotating and you can't get the moment at any point. So that's the general pieces that we have in this chapter. If you understand each one of these, chapter 17 is done. If you understand this, curvilinear translation, fixed axis rotation, and general motion, you know how to use these equations. You understand your problem. I'm not gonna say in your problem that it's a fixed axis rotation. You need to understand it by yourself. Once you knew it's a fixed axis rotation, so you will go to the, I'm not sure if it's in the equation sheet or not. Did I give it back to you? So let me show, let me see, sorry. Okay, I'm gonna show you. I don't have it here. But I have the general one. I have the sum of f equal to ma, but you should know that ma can be x and y if it's translation, can be n and tangent if it's curvilinear, and also has the moment. So you can, it has the three equations that are general, but doesn't tell you what is each one belongs for. So you need to understand how you can do it. Okay, so I'm gonna ask you a question just to make sure that you understand. If we have, by the way, what I'm gonna put here right now, it's called a frame system. All right. Okay, so if I have a hinge here and I have a hinge here, we call this frame. Like we use this frame system. Like if you go to Walmart, you will find a very huge truss, and this truss is connected by columns, and these trusses are distributed every. Like if we look at Walmart, something like this, you'll find it. Or any store. So you will find a frame here, and there's a foundation for each frame, and this is like a truss, a concrete beam, whatever systems you are going to use, and they have another one, so that you can cover the whole system. And that's what you do when, if you are a structural engineer, any building that you go at, you look at the system. Oh, that's a truss system. This is something. This bridge is what is this system? It's a post tension system. So that's what you need to look at when you go to any structure, because you are a structural engineer. You need to understand how these systems, what kind of systems that you are using. So the frame, I can take one and I do analysis to one. That's what we do. So, but as a mechanism, if I make this a hinge, not fix it, like not connect it together, like I made a hinge like this, and I made a hinge like this is not a structure anymore. We call it unstable structure. But in mechanics, it's not unstable, it's a mechanism. It's something that we need to look at. So let's look at this beam, the one on the top. It's supported by this column and this column. And let's say that there is a force applied on this structure this way. What is going to happen? How this structure is going to behave? This beam is going to move, right? Like, what is the course of movement? It's going to be circular, right? Around, this is going to move this way, and this is going to move this way, right? Tell me, what kind of movement that this beam is going to have? Is it going to have linear translation, curvilinear translation, fixed axis rotation, or a general plane motion? General plane motion? Do you tell me that? What do you guys say?
I think
Fixed axis rotation. Fixed axis rotation means that it's fixed from one point and it's rotating about this point. So actually, this beam is moving. It's not fixed from any point. Like this point is moving and this point. Every point is moving. Okay. So it's a translation. It has a translation part of it. But fixed axis rotation doesn't have any. Like it's a fixed. Okay. So this actually is a curvilinear motion. How? This beam is moving this way on a curve. Like if this is moving, it doesn't move about itself. It just moves on a curve. That's what this beam is doing. This beam is gonna go this, and goes up the same way. So and that's why what I'm telling you, you need to understand the problem carefully. Giving you something like this, because you know this, but you need to understand how is the movement so that you can apply the equation. Once I knew this, that is a curvilinear motion, I can say that mg is equal to 0, alpha is equal to 0, omega is equal to 0. So that's just gonna solve a huge part of the problem. Okay? So that's part of it. So let's solve a problem similar to this one. Okay, so we have something like a swing, something like this. And I have okay, so I have a beam, like it says a 10 kilogram, 100 kilogram beam BD. So I have here's A, B, and here's C, and here's D. And here's definitely there's a hinge that hold this bar and hinge that hold this bar. So I have a 100 kilogram beam BD shown in figure 17. It's supported by 2 rods. So I have these 2 rods having a negligible mass. So these 2 rods, AB and CD, having a negligible mass. So you don't want to account for the masses. It's very, very little, maybe a few grams. But the big beam is the huge one. Okay, so what I'm asking for, determine the force developed in each one of these rods. So I want to know the force in AB and the force in CD. And from what I can see, what I can relate to the forces in 2 bars, I can tell that both of them should have the same forces, right? Because it's symmetric. So the force here should be the same as the force here. Alright? So I'm giving you that this started when theta, so this is the starting point. Theta is equal to 30 degrees, and this is very important. Why? Because the force in this rod is it changing with theta. In this rod, the force has an x and y, but when this comes vertical, it's gonna have Fy, but right now it has Fx and Fy. So that's why I give you the instant that we are looking at. And I'm telling you that the omega of these is in this direction. So this is the omega of these 2 bars. And omega is equal to 6 radian per second. Okay, so let's solve this problem. Alright, so what I'm looking for is this beam. So what you have to do is first identify what kind of motion that is this beam is doing. Is it translation, curvilinear translation, fixed axis rotation, or general plane motion? Curvilinear, why? It's the same thing like this train, right? It's just this part is moving, so it's moving around a circle, or it has a curve. Okay, so you take this beam out, and you will do what we are going to do for all the problems. You will draw 2 things, the free body diagram and the kinetic diagram. I told you what we do in the free body diagram.
So if we were just focusing on the AV piece, right, and like the rest was gone, that would make it fixed axis rotation.
Yeah, that rod is fixed axis rotation. We can talk about after we solve this problem. But right now we are focusing on this beam. Yeah, but you are right. It's going to be fixed axis rotation. But yeah, so let's do the free body diagram. You guys tell me what forces that hold this beam. What are the forces of this beam? How this beam is holding itself? Yeah. What is it? The 2 tension. Excellent. So I have 2 tension. I have TAB. Let's say TB. TP. And I have, by the way, the direction is very, very important because I'm looking at this instant. So I know that the direction is something this way. So this is TD. Okay, 2 forces. What else? Weight, I have 100 kilograms. So the weight is always at the CG. So I have W here is equal to mg, which is 100 multiplied by 9.81. Okay? So I have these forces. let's look at what we put in the kinetic diagram. You guys remember?
The rotation.
The movement. Excellent. So for the movement, what kind of movement that I have? Look at this. So you always have the movement in your head. So I know that this point is gonna move this way, and this point is gonna move this way. So all the points on this body is gonna move this way. So the movement, since I have curved linear, so I'm talking about tangent normal. And since the omega is this way, so I know the MA tangent is this way, and the normal is this way. Okay? Right? And I don't have moment, because it's curvilinear translation. So I'm having MAN this way, and MA tangent this way. This is the movement that I have. Okay, so once you draw free body diagram and kinetic diagram, you get almost 30% of the points for this question, if you draw them right. Okay, let's get the rest of the 70 points. The rest of the 70 points is that you need to put the equation. You need to show me that you know the Newton's second law. So the Fn is equal to MAN. And let's apply this. What is the forces in the direction of the AN? TB. And let's say this is the positive direction, right? So I have TB, and what is next?
And TB.
And TB. Here I put the A and C differently, but it's the same concept. TB. What else?
The weight has a
The weight has a
right?
component, so I need to find the component in the end and the component in the tangent. So I know theta, this is theta, right? This is theta, and I have this as a theta, so I have here W cosine and W sine. What is the component in the direction of the normal? Is it the cosine component or the sine component? Sine. Is it positive or negative? So I have W cosine 30 is equal to M A normal, right? I can't get A normal. Why? Because I give you omega. If you know omega, you have this bar like this. And if you want to find A normal, we know that A normal is M multiplied by omega squared multiplied by R. If you guys remember, AN is V squared over rho, which is R, and we know that V is omega multiplied by R, and all the squared, this is R, so it's gonna be equal to omega squared multiplied by R. Okay? Right, so we know omega squared, we know R, so we can get this one. So let's solve this. So it's gonna be TB, which I don't know, plus TB, that's what I'm asking for, minus W, which is 100 multiplied by 9.81, multiplied by cosine 30, is gonna be equal to the mass, which is 100, multiplied by omega squared. Omega squared is 6 squared, multiplied by the radius. The radius, I give you the dimension here. All the dimensions are given. This dimension is 0.5 meter, and this dimension is 0.8 meter. Okay? So I give you the radius. What radius I'm gonna use is this radius. So the R is 0.5. And once I solve this, I can have TB plus TD minus A for 6.9, 9.6 is equal to 1800. Alright, I solved this, but I can use my sense and say, okay, TD is equal to TD, so I can say 2T is equal, and I can get T. But let's do it with the F tangent, like we can get it through the, not every tangent, actually we can get it through the moment. But if you get the moment here, about this point, like here, I know that the moment is equal to 0, there is no moment. If you get the moment here and the moment here is 0, but here there is no moment. So if I said that the moment, let's write it here. Sum of the moment at G, I know it's equal to 0. Why? Because of this. I did it a few moments ago. So the moment about G, the W is passing through G, so the moment of the weight is 0. So I'm ending up TB and TD. However, if you get the components of TB and TD, you will have a component in y and a component in x. The component in x make a moment equal to 0 because it passed to the point that I take the moment at. So I will end up with the component, the cosine component of these two forces. And let's say that we are gonna take the positive moment, let's say this way. All right, you tell me, TB is gonna have directions like this. Is this gonna make a positive moment about G or a negative moment about G? It's gonna be this way. It's gonna be negative. My positive is the other way. So I have negative TB cosine 30. This is the value of the force. What is the R? The R, I have 0.8, so 0.4 and 0.4. So I multiply by this arm, which is 0.4, multiplied by 0.4. How about the other force? It's gonna have TD, and this is gonna be positive. TD cosine 30 multiplied by 0.4. The W is going to be moment equal to 0, and all this is equal to 0. Yeah, because I put it here, and G is equal to 0. I got all the moments, and I put them equal to 0. We can divide by 0.4. We can divide by cosine 30. So we'll end up with TD is equal to D. So we prove it, but you know from the engineering sense that the arcos are equal to each other. So right now I can come back and solve this equation and say that 2T is equal to 1800 plus 849.6. So the T is equal to, or we can say TB equal to TD is equal to 1324.8 Newton. Right, so right now we solved the whole problem. Also, I solve a problem on rigid body translation. I'm gonna solve a problem on rigid body fixed axis rotation. But I want to tell you one thing about fixed axis rotation. We put, actually the fixed axis rotation was here, right? Right, we put something like this, right? And let's say, and what we did actually a second ago, we said that it's been here and been here at the CG. And if you have a system of forces F1, F2, F3 outside, and you have any moment on this body, something like this, and here this body doesn't move, it only has I, R, multiplied by alpha. That's what we did. That's the free body diagram, it has all the forces, but also you need to put the reactions, R, Y, and Rx. Because all these are still forces, free body diagram. Because without these two reactions, that means that this is not here. Because these two that balance the outside force from the movement. And this is the kinetic diagram. Alright, so we can I have it tangent, but also we can keep it tangent like okay. I'm gonna put another example. This if it's spin here. But what if my body's like this and it's spinning here? Here is the fixed axis rotation. What is gonna happen in this case? In this case, if you have it's a fixed axis rotation, and here's the CG, and here's the CG. Let's put all the forces. All the forces is gonna be something like this. F1, F3, and F2. And the reactions is down here. You have Ry and Rx. And this one moved, right? This point is gonna move because it's gonna rotate. But how is the movement look like? It's gonna be something, for example, you are gonna make a line like this, it's moving this way, so you'll have MA tangent, and this is the normal, MA normal, right? And it's gonna have, for example, like if it's gonna move this way, it's gonna have I bar multiplied by alpha at this point, okay? So this is how the movement look like. You will tell me, okay, you told me that there is no translation here. I told you no translation here. Here's all the fx and fy is equal to 0 because this point doesn't move. But if you told me what is the movement here, this point is moving because this is rotating, and here is gonna be have ma tangent, and here you're gonna have ma normal. Okay? So what I'm saying is these equations apply at a specific point that we're looking at. If I'm applying the equation at this point, the point here, sum fx, sum fy is equal to 0 at this point. But at any point, there is an acceleration and there is rotation. So at this point there is, at this point there is. So it's based on the point that you are looking at this one. Alright, so let's write these equations. So I can say that the sum of fx at, for example, this point is 0, but if I'm looking at fx or f tangent, let's say f tangent, at the CG, f tangent at the CG is equal to ma tangent. F normal at the CG is equal to ma normal. And if you are looking at the moment at the CG, here, sum of the moment at G is equal to I bar multiplied by alpha. So this is the equations at the CG. So we still have them. But if you want to find the moment about this point, it's something different. Like let's name this point O. So the moment about O, I need to take the moment of this and this. I need to take the moment of those two, right? I still have I bar alpha plus, how about the moment of m multiplied by a tangent? A normal, sorry. Does this force make any moment? MAN? No, why? Because it passed through the point that I take the moment at, this one. Okay, so this force doesn't make any moment, but this force makes moment. This is the one that moves the body. Okay, so I need to take the moment of this force, so it's gonna be RG, this is G, with respect to point O, cross product M A tangent. Vector is gonna be something like this. Once I expand this, and this is at the CG, so I have to put bars here. So this is gonna be I bar multiplied by alpha plus R G with respect to O crossed by the mass. And if you expand A tangent, if you guys remember, A tangent is equal to alpha multiplied by R, or R crossed by alpha. Alpha so it's alpha multiplied by R. So it's gonna be alpha crossed by R. And when you do, you get the magnitude. Let's forget about the directions. Let's remove all these vectors. So this is gonna be end up with n multiplied by alpha multiplied by R squared. So this is gonna be I bar multiplied by alpha plus R multiplied by M multiplied by alpha multiplied by R. This is the mass multiplied by alpha multiplied by R squared. And this can be M R squared multiplied by alpha. So if we put all this together and I take alpha as a common factor because it's here and here, so I take alpha, I will end up having I bar plus the mass multiplied by R squared. So do you guys remember what is this quantity? I bar plus the mass multiplied by R squared. This is the parallel axis theory. The y-axis here, you have I bar plus the mass with the distance squared to the point that you are taking the moment at. So this actually, the moment of inertia about point O. So this is the moment of inertia about this point. So what we did is we transferred the moment of inertia from the CG to the moment of inertia at this point. Okay. So right now I can say that the moment at point O, let me write it here. The moment about point O is equal to alpha or IO multiplied by alpha. So we have the moment at G is the I bar or the ICG multiplied by alpha. The moment about any point, you get the moment of inertia at this point. So you move the inertia from here to here and multiply it by alpha at any point. So that's also a general rule. So what I want to do from this, I can say here that the sum of the moment at any point O is I bar multiplied, sorry, not I bar, it's IO multiplied by alpha. Okay, so that's what I want to prove from that. Next time I'm gonna solve a problem. So what I did in new here, I just proved to you that these equations, this is the general equation, but the moment at any point O is equal to the I at point O multiplied by alpha. If you are getting the moment about the CG, so the I at the CG multiplied by alpha. Okay, so next time I'm gonna solve a problem, an application of this, and I'm gonna end in chapter 17 possibly. And so you will have to do your part. Please do the plan that that I told you about, so that we can catch as much as we can under revision for the final exam. For who came late, the final exam is on Thursday next week from 9:30 to 11:30. It's gonna cover the entire class, including the fluid dynamics and also the structural dynamics. Okay.
Professor, is it gonna be in the same room?
Yeah, the same rule. Right, so, Harry?
Zero?